questions as we go. Don't feel like you need to wait for the end if anything's unclear. I'll also pause as we go along. So this is joint work with Unai Fischer-Abaigar and Christoph Kern, who are both at the University of Munich, are fantastic collaborators. And the topic of today's talk is motivated by the observation that increasingly algorithmic predictions are used to guide human decisions, and specifically the way we allocate public goods. So to give a few examples of the kinds of problems that I'm talking about, in education, over half of US high schools use predictions to understand what is the likelihood that an individual student is likely to graduate as a means to understand who gets to see a counselor and receive extra resources. Right? So we're using prediction to try to understand who should we put into these after-school slots with the aims. In public health, we predict disease to understand who gets to see a doctor. This happens at a national scale in places like Israel. And even for domains like climate monitoring, public agencies are interested in understanding what is the likelihood that the particular factory will pass inspection to most efficiently allocate inspectors in a large population. And the thing that's interesting to me throughout these different problems is that predictions are really a means to an end. We don't really care about the prediction per se. We make these predictions to help make better decisions. But at the end of the day, what we really care about is improving some kind of context-dependent notion of welfare. Like we want to increase graduation rates. We want to raise life expectancy. We want to make sure that the air is cleaner wherever we live. So if prediction is really this like sub-piece of a broader system in which welfare, not accuracy, ultimately determines success, how do we price and understand and contextualize the value of a predictive algorithm? So we'll try to unpack this question a little bit as we go along. So the way I think about prediction in these kinds of allocation problems is that the predictor tries to solve some kind of subset selection problem. So we'll use this school example as the running example. So we have a very large population of students, and we can't get to know each student individually. So we want the predictor to kind of help solve this question. Find me the best group of students to spend my limited school resources. And if we can improve the predictor, we can clearly improve our decisions, right? So maybe we have a model that's more accurate in telling us who's going to drop out and who's not. And hey, we should interview on these students with the green arrows rather than the red arrows. And by that, we'll be making better decisions around who to intervene on. But if we really care about graduation rates, there's lots of different things that one could be doing, right? So in particular, to improve how many children graduate from school, we could, of course, select a more suitable set of students to intervene on by improving our predictor. That's kind of what we discussed in the previous slide. Or we could simply choose to hire more counselors, right? We're solving some kind of constrained optimization problem, and we can try to just, instead of paying money to improve our predictor, just hire more counselors and intervene on more students. Or we could invest in better counseling so that the students who do see interventions just have bigger changes in their educational outcomes. So to me, these are three key policy levers that are present in all these kinds of resource allocation problems. So we can improve prediction, we can expand access, or we can invest in quality. So the theme for today's talk is that given that there's this broad design space of things that we could do, what lever is the most cost efficient? Like when is prediction a high order bit? What is the relative value of prediction relative to these other things that we could do? And kind of cutting to the chase, the main result of this line of work is that when it comes to allocating scarce goods, the benefits of expanding access and simply treating more people often outweigh the benefits of improving prediction. So said otherwise, for these kinds of resource allocation problems, prediction is often a lower order bit. And so this idea will develop formally throughout the rest of the talk, but to give you a little bit of intuition, discussed how prediction is really used as a way to kind of solve a subset selection problem. We peer into the prediction crystal ball to assign risk scores to individual students as a means to rank them according to their need. And once we factor in resource constraints, we always intervene on the students who we believe are most likely to drop out. And by improving our predictor, we can try to resolve, like, is this student with a 0.86 really 0.86, or is it 0.88? And should this student fall to the left or the right of this line of people to the left of the line receiving interventions? But at the end of the day, while these predictions drive better decisions, the welfare improvements of improving a predictor often pale in comparison to just simply treating the next person. So the talk for today will kind of develop this idea, and I'll have three main parts. I'll start by providing some background and setup that just tries to set up this formal model that we'll work with. Then I'll present several theoretical insights in kind of stylized settings. And then I'll present an empirical case study that looks at identifying the long-term unemployed in Germany. So getting started with the background. The kind of problem that we're looking at is that there's a social planner that's aiming to allocate a scarce amount of resources. And to do this, the planner has data on people who are described by pairs X and W. So X is features that describe the person. So for this school example, we make these predictions using things like demographics or previous academic records. And the thing that we're predicting is, like, what is the effect of someone receiving an intervention? So for instance, what is the change in their probability of graduation were they to receive extra tutoring? And so given a distribution over these pairs, or a population of students, the planners tries to maximize average welfare in their population subject to a resource constraint. Right? So we want to maximize graduation rates subject to the fact that we can only intervene on a subset of students. And more formally, the optimization problem looks something like this. We're trying to decide on a policy pie, which maps features to decisions, like, does a person receive a good, yes or no? And we have this constraint that we can't say yes more than an alpha fraction of the time. So here, this alpha parameter is a constraint that says what fraction of the population can we intervene on? Can we intervene on, say, 1% of students or 10% of students? So alpha is a number between 0 and 1. As one might imagine, this kind of optimization problem has a very simple solution. You simply do what's most intuitive. You predict the welfare improvement. So for every individual student, you predict what is likelihood of, what is the expected value of W. And then you intervene on students in the top alpha quantile. So you sort of give resources to the people who have the highest predicted effects. So this makes a lot of sense. You just predict effects, sort them, and intervene on the top alpha fraction. Great. So given this setup, we try to formalize the value of prediction by introducing this concept of the prediction access ratio. So the prediction access ratio is a ratio. It says, it's the ratio of what is the change in optimal welfare that comes from increasing access and treating more people. So what is the value of the optimal solution of this program if we increase alpha, versus what is the change in optimal welfare that would come from improving our prediction. Right? So it's just a number that tells you what is, if it's bigger than 1, we're better off increasing access, and if it's below 1, we're better off improving prediction. In particular, calculating this prediction access ratio is a fundamental step towards deciding what to focus on. In particular, if we want to,
Yes, sorry. Can you, so I'm curious, what is access in this case? How do you define access again?
Access is this resource constraint, alpha. It's like what fraction of the population gets treated. So am I treating 1% of so changing in the welfare that comes from increasing access is, say, like, what would the value look like if instead of alpha being 0.01, it was 0.02, and I could treat 2% of people rather than 1% of people? Great question.
So can we think of it a numerator term as an intervention and comparing it with the usual way of conditioning in the denominator? Is that correct?
I couldn't quite hear you.
So when you're increasing access, that means we are intervening on the access level, right? Maybe that the W.
Yes, and keeping our predictor fixed, yes. And improving prediction, keeping the resource constraint fixed, and we're improving, say, like the R squared of our model. And I'll try to make this precise over the next few slides.
Okay, got it.
So the main idea here is that what this prediction access ratio is a fundamental thing to calculate when we're deciding whether we're going to improve access or prediction. In particular, we only need to factor in costs, right? So once we factor in costs, we multiply the prediction access ratio by this ratio of costs and decide whether this is strictly smaller, or larger or smaller than 1. Right? So if it's larger than 1, we're better off increasing access. We get better bang for a buck from increasing access. And if it's smaller than 1, we get better cost benefit improvement from improving our predictor. So this prediction access ratio is this the term on the right. So informally, the prediction access ratio measures relative counterfactual changes on social welfare. It tries to answer questions of the form, what would graduation look like if I could intervene on 1% more people, versus what would graduation rates look like if my predictor explained outcomes 1% better, okay? So this is exactly sort of another way of looking at what does this change mean. And more formally, we can define this prediction access ratio as follows. So define V star of alpha and gamma S to be the optimal solution of the resource allocation problem, where we intervene on an alpha percent of people, and our predictor explains a gamma squared fraction of the variance in outcomes. So both alpha and gamma squared are parameters in the unit interval. So R squared varies from 0 to 1. The prediction access ratio says, what is on the denominator, we have the welfare after collecting more features or collecting more data that together explain a delta fraction more of the variance. And we're subtracting off the current value of optimization problem. And in the numerator, we have what is the welfare if we instead increase alpha by some fraction, but by some constant delta. So here I fixed delta to be the same, but in general, you can have this vary. But for the simplicity, we'll just keep them fixed and equal to each other. Questions about the prediction access ratio so far?
Yeah, I was interested in, because there's a couple of different things here for a prediction. Like is this like a goals-based prediction, or is it that we're measuring the relative counterfactual changes to their social welfare? So is it like, what are we basing the increase or decrease on?
So we have a well-specified target of prediction. This is like this welfare improvement. And the improvement in prediction is a reduction in or an improvement in the explained variance of this outcome.
Okay.
Yeah, I think it'll be, I think it may be a little bit more precise in a second.
Thank you.
Great. So with that out of the way, I'll present some theoretical insights that tries to quantify exactly this prediction access ratio in a number of different settings. So in particular, I'll present 2 sets of main results for 2 different models. One is a linear causal model, and the other is this worst off identification model. So starting with this linear regression case, here we assume that the welfare improvement is equal to this causal treatment effect. So the example to have in mind looks something like the following. You're trying to allocate a resource, like a finite number of after-school tutoring slots. And the improvement that you're trying to predict is what is the change in the probability of graduation if I were to assign a student to this tutoring slot. And we'll make the strong assumption that WI, so this change in potential outcome, so YI1 is the graduation likelihood under the graduation outcome under intervention and YI0 is the graduation under no intervention, is equal to this linear function of features, linear function of some features X plus some noise. Right? So this is like the linear causal model that's very common throughout quantitative social sciences and econometrics. It's kind of like a basic place to start to try to understand this problem. And here, we can very precisely characterize what this prediction access ratio looks like. In fact, in this linear setting, if your predictor has an R squared of gamma squared, then the prediction access ratio, so this change in graduation rates that would come from a 1% increase in the access to tutors versus a change in graduation rates that would come from a 1% better prediction, is exactly equal to the square root of the variance explained by your model over the level of access. So more formally, the theorem contains, I proved upper and lower bounds that match up to a small universal constant that exactly characterizes what this ratio looks like for this specific model. And okay, so we calculate this ratio. What exactly can we do with it? I think the way I like to think about this result is that it gives this definition or tries to operationalize this idea of what does it mean for a predictor to be good enough for decision making. I feel like a fairly lowbrow definition of what it means for a predictor to be good enough for this kind of resource allocation problem is that we're actually better off not touching the predictor and improving its R squared, and instead focusing on other parts of our design problem, like in spending access, right? So if I get better bang for a buck from doing something else, my predictor is good enough, right? So the theorem gives you sufficient conditions. So kind of going back to maybe the setup, a predictor is good enough if the prediction access ratio times this ratio of costs is greater than 1. It's another way of viewing this condition. And the theorem gives exactly like sufficient conditions for this predictor to be good enough. In particular, it says, leave the predictor fixed and expand access as long as the square root of your variance explained is greater than this ratio of cost times your current level of access. Okay, so there's something, it's like a number that this equation, you can check it based off observed statistics of your model and try to decide what makes sense to focus on. I think this idea is best understood visually. So we'll show you this plot. So here I'm showing you a plot that we're on the x-axis. I'm plotting the level of access. So am I treating 2%, 4%, 8% of my population? And on the y-axis, I'm plotting the square root of the R squared of my model. So does my model explain 10%, 20%, et cetera, of the variance? And the colors describe this prediction access ratio times the cost ratio, where I've fixed the cost of access to be twice those of prediction. We can play around with this. And the black line is the level set of points for which this number is 1. Okay. So pairs of points alpha and gamma s correspond to particular states your resource allocation system could be operating in. And points above the line are those for which its prediction access ratio times the cost ratio is greater than 1, so we're above the block line. And in this regime, expanding access is cost efficient, and the thing that we should try to do is to move right on the plot, right? So here we're saying, actually, we get a much better bang for buck from improving our access, so we're going to keep our predictor fixed and try to increase alpha. And the opposite is true if we perform this calculation and our value is below the black line. Here, improving prediction is cost efficient, and one should aim to move up on the plot, right? And try to improve the R squared of your model. So intuitively, this prediction access ratio, what it does is that it gives insight into what kinds of local improvements make the most sense, right? The kinds of problems that I had in mind when thinking about this definition is you think about a budget director or a policy director for like an education system or a health system or any one of these kinds of resource allocation problems settings that I was talking about. And at the end of the year, they say, hey, I have some money left over in the budget. Our current system treats X% of people and explains Y% of the variance. I'm a very busy person, but what really should I focus on if I aim to maximally improve welfare? And at least for this linear setting, the answer seems to be that you should improve access if your square root of your variance is greater than your current level of access. Otherwise, you should spend money on your predictor. So I'd like to summarize this result by saying that kind of prediction and access roughly go hand in hand. the variance explained by your model should roughly always be equal to the level of access that the number of people that you're treating. Okay. So I think that this result's it's not counterintuitive, but perhaps it's counter-narrative. In particular, it can make sense to expand access even if your predictor explains almost none of the variance. Right? So I think that a thing that often happens is that we have some predictor of life events like graduation. And typically these are not things that we can predict perfectly, right? We might only be able to have like some small non-trivial accuracy or an R squared of say like 0.2. But this kind of tries to flip this result on its head and say, actually, models that even give you a weak signal can be good enough for these kinds of decision-making problems. So summarizing the takeaways from this linear setting, access and prediction really go hand in hand, right? You should kind of grow access and R squared together. And in particular, prediction becomes less valuable as goods become more scarce. Right? If you're treating very few people, you're actually much better off improving access than you are improving prediction because you're kind of in the very left side of this plot. And you don't need to predict something very accurately to act upon it effectively. Any questions about this first part?
Yeah, I have a question. You were talking about access to providing access, right? Like it's kind of performing intervention and then finding treatment effect. Are you considering the impact of confounding variables where you need to adjust to find out?
So great question. Here in this linear setup, I'm not worried about confounding because I set up like a well-specified model. Right? Like you could think about this as like having RCT data, where I'm making the strong assumption that this welfare improvement is exactly a linear function of your features, data is Gaussian. So I've made things sort of very simple, so I don't have to worry about confounding. As just, I guess, a place to start. We'll think about more realistic settings in a second.
Yeah.
Good question.
Thanks.
Great. So now we'll think about this second model that looks at a kind of different, somewhat different prediction problem. So oftentimes we use prediction as a means to identify those most in need. So here the running example will be, think about you're an employment office in a state like Germany, and you want to use prediction to understand of the people in your population, who is going to be likely to be long-term unemployed. I want to make sure I surface those people so that they receive treatment or at least receive attention. But here I'm really focusing on this question of, I just want to identify this population that's in need. I'm not necessarily concerned about changing their outcome. So here on the right side, I'm plotting the histogram of unemployment durations for incoming job seekers in Germany. And this cutoff of the red dotted line is the set of people, it's like 1 year. So everyone to the right of this line is unemployed for longer than 1 year. Right? So I want to use my predictor to understand of my large population, who's likely to be unemployed for longer than a year, who's likely to find a job in a short amount of time. Okay. So in this setting, we have some outcome Y, which we think of as the notion of individual need, right? So in this unemployment setting, Y might be the number of months that someone might be unemployed. And what the social planner tries to do is that it tries to identify the top beta quantile of this distribution. So we want to figure out who's in this right tail of the distribution. We want to identify everyone whose outcome is larger than some threshold that depends on beta. So to do this, the planner makes predictions y hat of this outcome y, and we choose to screen someone and prioritize them for attention if their predictions lie in the kind of top larger than some threshold alpha. Okay. So here, resources is equal to the number of people that I can process through the system. So what is the bureaucratic capacity? How many people can I actually pay attention to? And the value of the identification system is equal to of the long-term unemployed, of everyone who did experience long-term unemployment, how many did I actually screen? So visually, we can think about this kind of scatter plot, where the y-axis is the outcome that we care about, and the x-axis is the predictions that we're making. And we want to identify all of the points that I fall above this purple line, right? So these are all the people who we've determined to be in need. And the value of our system is of all these people, remember, we screen them if their predictions are above some threshold T of alpha. So the value is how large is this upper right quadrant relative to the top purple side, the purple shaded area, right? So the long-term unemployed, how many do we screen? And here I want to kind of disambiguate between two quantities, right? There's two distinct things, right? There's how many people we can screen, what is the capacity that we've built in to identify the long-term unemployed, and then there's the normative goal of how many we want to screen, right? So we might want to screen everyone who's unemployed for over 12 months. That might be equal to, say, 10% of the population, but we might only have capacity to screen 5%, right? We don't have the budget to identify we simply do not have the manpower to treat everyone. Or so alpha in this case is smaller than beta. Or we might be in the opposite situation in which we say we want to identify the bottom 10% of people, the 10% most in need, but we know that our predictions are not perfect. So we want to allow ourselves some wiggle room, and we're actually going to screen 20% of people with the aim of making sure that we identify the bottom 10%.
Can I ask another qualitative question there? Because I am really interested in this for the census that's coming up. I've been paying close attention to that because, like, for me in this example, what if some of those people are actually doing great and they're just not working because they found a financial situation with a partner, or they had a generational wealth come suddenly in there? Like, how can you separate from the unemployed who are resource scarce and the unemployed that are independently wealthy?
Great question. So at the end of the day, you really need to be careful about what is this 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 metric this outcome you're trying to predict, right? Is it just unemployment, or is it unemployment amongst those who are actively seeking a job? Right? If we define things, so here I'm thinking about unemployment of those who are actively seeking jobs, but I agree with you that there's an important first step, which is to make sure that the outcome that we're predicting is the outcome that we really care about, right? Because if there's misspecification there, then there's other issues. And I think that's a very interesting question that is a good thing to think about for future work. We should get to that.
So I have a follow-up question on that. And I think this is the most difficult part of making the right prediction, right? Because typically the data that we collect, if it's not from randomized experiment, is always, confounded by something, right? And I mean, that problem, I think, can be solved by maybe careful experimental design. But I think in most cases, when we make prediction, we typically use observational data, right? When we train this model or fit these statistical models. So I don't know if you have maybe whether it's possible to, take into account the fact that, you may not always get the right causal estimate of the prediction.
Right. So there's a whole set of issues when we want to predict treatment effects. I guess for this specific model that I'm talking about now, I'm not worried about treatment effects, right? I'm just thinking about there's some outcome like months unemployed, and I just want to identify everyone who's going to be unemployed for a long time. I'm not necessarily thinking about the case. Because that's the normative goal I've decided for myself. I'm not worried about, can I actually change their unemployment status?
So if you let's say you wanted to separate signal from noise, would it be mathematically incorrect in this model to then go and look at rates of homelessness, depression, suicide, addiction, or other social ills that might result at the end of long-term unemployment, maybe from like a social determinant of health perspective. If I know that a bunch of people are houseless and suffering from malnutrition, would that, and then I looked at it against this, would that make my prediction more accurate?
I'm not sure I completely follow the question. Is the question here that
Like,
you're
so
asking, like,
if somebody's long-term homeless, right? And I'm looking at
yeah.
that and I can't separate what I asked earlier, which is like, which of these people are willingly or happily unemployed? And then you said that it was long-term homeless. Then if you wanted to double check and make sure you weren't doing like a misattribution of that prediction, could you check it against other qualitative,
Sure. So yeah, you can, to understand whether you've picked the right, like, kind of outcome to predict, you can of course try to cross-reference that with other observable features of the person. I guess here I'm not specifically paying attention to that problem. I'm just thinking about kind of like a simple setup where I've decided, I've correctly specified the thing I care about, and now I'm trying to understand, like, what is the value of prediction in this case? Like, how much do I get from improving access versus improving prediction? These kinds of proxy variables are interesting, but not exactly
so
what
it's outcome based. I see. Thank you.
it's outcome based. Yeah, great. These are all excellent questions, so happy to talk more. Great. So for the theory in this, at least for the second part, I'll assume that both outcomes and predictions are Gaussian, and sorry, I'll assume that the residuals are Gaussian, so I have Gaussian errors. The plot would look something like this. And here I'm trying to understand the value of two different kinds of decisions and how they match up. Right, so on the one hand, we can try to improve our predictor. This is the plot on the right. And if we improve the quality of our predictor, there's sort of less noise in our data and things look kind of more linear. And by virtue of kind of reducing the noise, more points would fall in this upper right quadrant, right? So we would be able to identify more of the points in that fall in this purple shaded area. Or if we can, instead of improving our predictor, we can improve capacity, right? And at this case, this amounts to kind of moving this threshold to the left. And by moving it to the left, like, naturally more points will fall there, right? So what matters, what would give us a better impact as a function of, like, our current design parameters is the thing we want to understand. And here, recent result with Unai and Christoph shows that when it comes to identifying the worst off, improvements in prediction are really a first and last mile effort. So we prove the following theorem. The impact we get from improving our predictor, a small change in prediction, this change is highest when predictions are nearly perfect or barely informative. So more formally, the difference in welfare, the change in the number of people identified from better predictions, this quantity that we had written down previously of, like, what does the value function look like if we increase the R squared by some constant delta, is maximized as a function of alpha and gamma when gamma is either 0 or 1, right? So even if our predictor explains none of the variance or almost all the variance in the outcomes. So questions about this slide? All right, so this prediction is like a first and last mile effort. But if we work in the regime where we expect to work in, that we have some model that explains some kind of not huge but not tiny fraction of the variance, then we're much better off improving access, right? Particularly if our predictor has an R squared of gamma squared, then for very small values of alpha, this prediction access ratio is lower bounded by 1 over alpha to the C. So C here is is a constant that's greater than 1. In particular, it's 1 over the fraction of variance unexplained in the outcomes Y. So the thing that's a little bit dense, but the thing that I really want you to take away from this slide is that the relative value of prediction is lower than it was for the previous setting. In particular, this comes from the fact that this constant C, for the linear case, it was always equal to 1, right? It was a gamma over alpha. And here it's 1 over alpha to some power that's larger than 1. So this prediction access ratio blows up faster as alpha becomes small, which means that we get much more improvement from expanding access than we do from expanding prediction. Questions? If we were to think about things visually and we try to redo the plot would now, you no longer have this kind of like diagonal dotted line. The curve at which we're indifferent between improving access and prediction is kind of this like nonlinear shape. And more importantly, there's like a much more region to the left, right? Like it's easier for a predictor to be good enough for decision making. And I guess we'll try to see how these ideas pan out for this real world example.
May I ask a question about if this is, because I think I have like like if it's related to goods, I'm kind of interested in like how does economic elasticity factor in, like if it means that there's like a variable that changes over time and it's dependent on other like they're not like welfare is like an emergent node of the system. So like is there a way to be able to like replicate like a study, if you were doing this for children like you said, is it just the ratio of percentage changes that is dependent? Like I'm trying to figure out which of the variables are independent or dependent, and like how might skew the data if you looked at elasticity instead of like a fixed concept of economic environment being stable.
It's a great question. I haven't thought so much about what happens if outcomes are networked or sort of socially determined, and where my outcome affects your outcome, or things change over time. I think these are all interesting extensions. How about we come back to that at the end of the talk, and I'd love to understand this point better. But I guess that's not something that's sort of dealt with in that theorem. Great. So with what time I have left, I wanted to move on to this last part of the talk and present this empirical case study on German unemployment. So
yeah, I think we're on track. Yeah, go ahead.
Sorry?
Yeah, sorry. I said we are on track. You can go ahead.
Okay. Great. So, this theory that I presented helps build intuition about what matters when. But here the question is, we try to understand, and how do we actually build a toolkit that allows us to study how do prediction and access trade-offs play out in practice. So here we'll run experiments using nationwide administrative data on German job seekers. So this was a collaboration with the Institute for Employment Research in Germany, where we had access to a 2% sample of all unemployment spells over the last 50 years for all German residents. So this contains over 62 million rows. So this is a kind of rich administrative data set that one would use in practice when trying to build these kinds of risk scoring systems to allocate resources and prioritize job seekers. So our work, we develop an empirical toolkit that allows decision makers to make principal design decisions around how to grow these allocation systems. So I'll tell you a little bit about this setup. What we did is we trained like the kind of machine tabular predictor that one would use in practice, right? So we trained a gradient boosted decision tree on historical data that tries to predict for an incoming job seeker what is their unemployment duration. So the outcome here is the number of months of future unemployment. And we did this the way you would do it in practice, right? Where you don't actually have IID data, right? You collect data historically. So we use training data from 2010 to 2014. And our test data is data that happened, or we tested on job seekers after 2015, right? So there could have been distribution shift here. Things could have changed, but this is exactly the kind of thing that we have to deal with in practice. So I'm trying to understand, what do these prediction access ratios look like? And here I want to focus at, this is very much out of theory bounds, right? For our theory made a lots of simplifying assumption around the fact that the data was Gaussian, that things were IID, that there's no distribution shift, etc. And here, of course, none of these assumptions hold, but somewhat surprisingly, we find that a lot of the insights from the theory exactly match up. So for this first experiment, what we did is we fit this cap boost model, this gradient boosted decision tree, which ended up explaining around 15% of the variance in outcomes. And this R squared of 0.15 is about what you would expect for various kinds of different life outcomes. It's like in the sort of ballpark, a normal performance. And now we try to understand, like, given this model, should we try to increase the R squared of our model by 10% or expand access by 10%? And this is something that we can do empirically. Because we have access to this test set, we can actually play out these counterfactuals where we increase a threshold or artificially reduce the magnitude of our residuals, and we can compute a plot that looks like this. So the x-axis here is the current level of access. So how many people are we treating with our model? And the goal is to identify the people who are going to be unemployed for over 1 year. So that corresponds to about 15% of the population. So beta is 0.15. And on the y-axis, I'm plotting the prediction access ratio. So this ratio that we computed empirically, this is not from the theory. But as predicted by the theory, we see that this prediction access ratio blows up non-linearly for small alpha. Our theorem predicted that this curve was lower bounded by something like 1 over alpha to c, where c is some non-linear c is greater than 1. So this is exactly what we see here. The prediction access ratio grows very quickly, which shows that if resources are scarce, expansions in access far outweigh improvements in prediction, right? So this prediction access ratio for small values of alpha is strictly larger than 1, right? So 1 is this red line here, which tells us we get bigger benefit from improving access than we do from prediction. In particular, we see that for this regime, it could even make sense to expand access even if we have more resources than are strictly necessary, right? So remember that we want to identify the bottom 15%, the top 15% of the population. And this right side of the plot that's circled here, alpha is strictly larger than 0.15, right? So we're already kind of over-resourced in some sense. But even if we have, because of these prediction errors, it could make sense. We could get bigger benefits from expanding access than we could from improving our predictor. So this kind of matches the insights that we see from the theory. At the same time, we see this other bit, that prediction is really this like first mile effort. If we instead were to consider a model that just predicts like the population average and explains 0% of the variance in outcomes, we can recalculate this prediction access ratio and see that this whole curve gets shifted down, in which case it's a lot more of the curve is below the red line, in which case prediction really does give us a bigger improvement. Okay. Questions about these experiments?
Did you choose the Gaussian model because of computational efficiency? Like why would you choose it over like a Bayesian model? Or if you're like trying to predict uncertainty, I'm really interested in.
Great. So we picked the Gaussian model because it was the simplest one we could analyze. So we were able to kind of, for the theory, And when we want to calculate these prediction access ratios formally, Gaussians made it easiest to think about these calculations for us. There could be other domains, other assumptions, of course, that one could consider. And I think that's a really exciting and interesting direction for future work, is to calculate these quantities under other kinds of assumptions or weaker assumptions, more general assumptions. But I guess I'd like to add that for this experimental stuff, there's no Gaussianity in anywhere, right? Like this is just all computed empirically off the real data.
Got it.
But I guess, you could be, it's kind of a little bit weird because, or it's interesting, I guess, that what we saw in the Gaussian case holds up in this empirical situation where things are not Gaussian.
Yeah. Interesting.
So the theory really provided some kind of like guiding insight here. So, and now I'd like to just kind of like wrap up. So the theme of this talk is that, when we're thinking about allocations and allocating social goods, prediction really is only a part of the puzzle, right? As like a machine learning researchers, we really focus on prediction, but prediction is just this sub-piece of this like broader thing. And we want to understand, the goal of this work is to try to understand how does prediction kind of match up and fit in with other design parameters like capacity constraints. When do prediction give bigger or smaller improvements than expansions in capacity? Right? So how do we contextualize? It's important when we're thinking about these problems to understand, to contextualize these different policy levers. But I really think that this is just the beginning of this kind of line of work. There's so many other things that one could be thinking about and trying to understand, not just prediction and capacity constraints, but details about how are these interventions allocated? Are they on a person-by-person basis? Are they on a group basis? How do these things fit in? How do these predictions and capacity constraints interact with caseworkers? There's so many more exciting questions to be done in this kind of prediction and resource allocation space. I think this is really just the start of a kind of hopefully multi-year research agenda. And I'd love to I think during this talk, there's been so many interesting questions and comments from the audience that, point out all these different things that we haven't thought about so far that I'd love to see people work on and learn about. So with that, I'd like to thank everyone. And I guess we have 10 minutes for questions.